is classified as a heavy metal commonly found throughout the environment in different forms. It is considered toxic to humans when exposed to contaminated food products such as fish or accidental exposure in nature. Due to the toxicity, instrumental analysis is fundamental in ensuring mercury levels in food tissues and water is safe for human consumption. In this presentation, two instrumental analysis procedures will be investigated. The first being cold vapor atomic absorption spectroscopy, CVAAS, followed by inductively coupled plasma mass spectrometry, ICP-MS, to analyze mercury content in water. Cold vapor atomic absorption spectroscopy is one of the most common techniques in analyzing mercury. CVAAS was first introduced in 1963. The difference between the cold vapor atomic absorption and the normal atomic absorption is that in the classic method, a flame is required to turn the sample into a gas, whereas in CVAAS, a flame is not required. Both organic and inorganic samples of mercury can be detected via cold vapor atomic absorption spectroscopy. Organic mercury must first be oxidized by an oxidizing agent, such as potassium persulfate, to form mercuric ions before entering the instrument. A reducing agent, stannous chloride, and the sample are then pumped into what's known as a gas-liquid separator. Pure, dry argon is added to the gas-liquid separator, which forces the mercury out of the sample as a vapor. Once the mercury sample is ready, it is carried through a reaction chamber, which is positioned through a light path of 253.7 nanometers as part of the atomic absorption spectrometer. The absorbance is then recorded via a detector at the end of the atomic absorption optical cell. The optical cell is made up of quartz, 10 centimeters long and 1 centimeter in diameter. Once the absorbance has been recorded, the unknown concentration of the sample can be identified with the use of a standard calibration curve from the known mercury standards. For testing mercury content in water, the use of cold vapor atomic absorption is used. This is because CVAAS has a working range between 0.2 to 20 micrograms per liter. CVAAS has a 4 times greater magnitude of sensitivity than a typical flame AAS. Modern instruments have been able to detect concentrations of mercury in the nanograms per liter. CVAAS can be used to analyze salt water, domestic water, and wastewater, providing there are no substances that may cause interference in the analysis.
The advantages of CVAAS include relatively cheap sample preparation, the ability to analyze a large sample, detection limits of just a few parts per trillion, analyzes sample in approximately 1 minute, requires very little operator interaction, and takes up just a couple of feet of bench space. While disadvantages include the inability to provide isotopic information on a sample. Inductively coupled plasma mass spectrometry, or ICP-MS, was introduced in laboratories in 1983 and serves as a vital tool in detecting minute quantities of rare earth metals. ICP-MS can be used to analyze a broader range of materials compared to CVAAS and specializes in a much narrower range. ICP-MS analyzes mercury in wastewater by first combining the mercury sample with gold and nitric acid to stabilize the sample. The gold acts as a strong oxidizing agent, which helps keep the mercury in the sample as charged ions so they can be detected. Then the sample is injected into the nebulizer and aspirated as an aerosol. Then the ICP torch separates the mercury sample into atoms. They are then separated again into mercury +1 and +2 ions as it enters the argon plasma. The ions then move from the ICP part of the instrument into the interface section, where the mass spectrometry begins. In order for the sample in ion form to be at the correct temperature and pressure, the ion beam goes through a sampler cone. The sampler cone is water-cooled, which cools down the argon gas, causing it to expand in the chamber. The pressure in the chamber is at 4 torr. Only a small amount of gas then passes through the second cone, known as a skimmer cone, into the first vacuum chamber. This procedure allows the sample to be at the right temperature and pressure for mass spectrometry analysis. The ion stream passes through the sample and skimmer cones into the mass spectrometer through to a series of charged metallic cylinders, which prevents the positive ions from repelling each other and moving out of the stream. There are 4 such cylinders forming a quadrupole. These cylinders alternate between AC and DC currents, forming an electrostatic filter, which only allows ions of one mass-to-charge ratio through, enabling the ICP-MS to provide isotopic information on the analysis. The ion beam then enters the detector and hits the first diode, which amplifies electrons, causing the ion beam to bend. A cascade of electrons follows as more ions hit the first diode and the subsequent electrons released hit more diodes, creating a pulse that can be detected via a detector. The major disadvantage of ICP-MS is the high capital cost of the instrumentation. The heavier elements, such as lead, are well suited for ICP-MS analysis, whereas lighter elements are prone to more interferences. Advantages to ICP-MS include the favorable detection limits, 0.01 to 0.1 micrograms per liter for many elements, simple specimen preparation, high output, about 40 specimens per hour, and the ability to measure more than one element simultaneously. Both instruments are used for analyzing mercury in water. The CVAAS is a more common method used as it is far more specific to mercury. The ICP-MS was developed later than the CVAAS and covers a wider range of analysis. The working range of the early CVAAS instrument was between 0.2 and 20 micrograms per liter, while for the ICP-MS, it has a detection limit of 0.001 parts per billion, making it more effective in detecting trace quantities of mercury than CVAAS. There is also little sample preparation required for ICP-MS compared to CVAAS, but the ICP-MS has a higher analysis speed. Up to 90 elements can be analyzed within 5 minutes. Overall, the technological advancements between the CVAAS and the ICP-MS has provided the ICP-MS with superior analyzing capability.